Thank you so much to the organizers for the invitation to speak with you today. We've already had have a big act to follow after Kathy's and Jared's talk, so we'll see how we go. This is my research group. So before I run out of time, I want to acknowledge the people who've done the work there in bold, and especially Adesh Kushwaha over here, who has done some of the stuff I'll talk about at the end, and who has a great talk coming up later in this session. Now, what will I talk about? Oh, I can see why Jared was confused with these buttons. Okay, first of all, I'll talk about light harvesting. And the first question I really want to get out of the way is, are there quantum effects in light harvesting? And I will argue that this is the case that only some kinds of quantum effects matter, and only some of the time, and in fact, rarely. And what we've done recently is classify possible coherent enhancements and develop recipes for engineering coherence. And so that's what I'll get to, but this kind of limits the scope of possibilities in this field. And then I'll give examples. In fact, I'll start by giving some of these examples of where coherent effects matter in light harvesting. And this is kind of how I got into this field, by looking at photosynthesis. And I'll try to convince you that delocalization matters there, and that it also matters in organic photovoltaics. And that once we put all of these examples together, we can engineer it in artificial devices, although that hasn't been done yet experimentally. So are there quantum effects in nature? We heard Professor Foley mention this at the beginning, and this is how I got into this field maybe 10 years ago, when there were papers coming out. There were some, they did experiments. This was at room temperature, which may, room temperature. This is liquid nitrogen. Well, maybe this was room temperature in Chicago where this was done. But there are some sort of oscillations when you do ultra-fast spectroscopy on light harvesting complexes. And the question for me was, all right, well, does this really matter in sunlight? Sunlight is not a femtosecond laser. And the answer is it doesn't, and I'll get to that in a second. But first of all, what do I mean by light harvesting? I mean, this is a conference on quantum energy, and light harvesting really is about converting the energy that comes from light into usable forms of energy. And in particular, in photosynthesis, we have architectures that in general schematically look like this. There's something called the reaction center, where you need the energy to get to, where it can drive chemical reactions. And that is surrounded by antenna complexes, which harvest the light. They absorb it to create excitations. And then the question is, how do those excitations make it into the reaction center? And so this transport of excitons from the antenna into the reaction center is an interesting question. It's fast, and this is where the quantum effects are meant to be happening. Now, this is a generic picture. This is just one example of what this type of architecture looks like in purple bacteria. In blue are the reaction center, and then these red and green things are the antenna complexes that surround it. So light will be mostly absorbed by LH2 complexes in green, and then hop around to the red ones, and then eventually into the reaction center. So the question is, how does that happen? But before I get to that, I really want to answer the question of whether light harvesting is quantum, because I get this question all the time, so I'm going to anticipate it. And the first point, and in some sense it's not, and the first point is that sunlight is extremely weak. It's not a pulsed laser, and in fact the absorption cross-section is only about 1 photon absorption per second per chlorophyll, so most of the time it's not doing anything. And what that means is that first, you can use first-order perturbation theory, and that means that 2 exciton events are negligible in sunlight. You can get 2 exciton events in a laboratory experiment, but they're irrelevant for performance if you want to convert solar energy into something useful. And this means that it reduces the scope for quantum effects like entanglement. This is what you get when you type entanglement into Google. It's meant to be an explanation. So many body effects, like many exciton effects, like entanglement, I will contend do not play a role in light harvesting. because sunlight is weak. And so what's left as a scope for quantum effects are coherences and superpositions. Now, some people don't like to call that quantum because you can have classical superpositions and coherences, and that's true. You could construct classical models of some of these things, but these are single molecules that are experiencing these things, so I will refer to them as quantum effects. And so the effects that can exist are coherences, and those kinds of beats that I showed you in those ultrafast spectroscopic traces, those are types of coherences. Those are time-dependent dynamical coherences, but the problem is that sunlight is at steady state. And so it turns out that sunlight is a stationary process, and that means that the molecular ensemble is also going to be stationary. Essentially, it's a heat engine of a type where it's connected to light, which is at a high temperature in a bath, at a low temperature, and it's converting some of that energy into what it wants. But it's doing through a stationary, non-equilibrium steady state. And because of that, there's no dynamical coherences in the ensemble. There's just a steady state density matrix. And this means the dynamical coherences, like the ones you might see in 2D spectroscopy experiments, those cannot have a functional role in light harvesting. So is there scope for anything else? There's no entanglement, there's no dynamical coherence, but there are some remaining effects that can play a role in light harvesting. And so even if transport is at steady state and with single excitons in weak light, coherent delocalization could and does influence the light harvesting efficiency. And there's two mechanisms that I'll get to this. I promised you a complete classification. I'll get to that in the end. But the one, I just want to start with an example. So we're talking about something concrete. The one concrete, which is the most promising example, is supertransfer. And this comes down, again, it's a coherent superposition effect. And so let me just kind of explain what I mean by superposition and delocalization. Suppose I have two molecules, and I have an exciton which can be on the left molecule or on the right molecule. When the molecules are coupled, the two eigenstates of the system are two delocalized states, where the wave function can be either in phase or out of phase on the two molecules, right? So here's a delocalized state that's a superposition of two localized states. So this is a coherent phenomenon because there's a definite phase relationship between the wave function on the two sites. Now, how does that affect transport? Well, in most kind of models of transport, of exciton transport in these systems, people use Forster resonant energy transfer, where let's suppose I have two donors. This is a classical process, so each of them emits the energy into the acceptor at a particular rate, which you can calculate. It's proportional to the transition dipole moment squared. If they're independent, these rates add up. But if there's a coherent superposition of the two donors, then from the point of view of the acceptor, it doesn't see two little antennas transmitting energy to it. It sees one large antenna. And this large antenna has a larger transition dipole moment. And if you work out the maths, you end up with the rate. This rate, which is still an incoherent rate, of transport is twice as large as what you could have gotten here if you didn't have the superposition. So the fact of delocalization can enhance the transfer efficiency, transfer rate, and this has been called supertransfer. For those of you from quantum optics, this is exactly analogous to superradiance, except that in superradiance, the emission is into the field, and here the emission is into the acceptor. And supertransfer happens, I will contend, in these light harvesting apparatus of purple bacteria, because if you zoom into each of these antenna complexes, you can see these circular symmetric arrangements of chlorophylls. You can calculate the Hamiltonian. It doesn't fit on my slide. But if you do that, the eigenstates are delocalized substantially around the ring. And you get a large transition dipole moment, which is much larger than the individual ones. And so if you have many of these ring assemblies, each of them with these large transition dipole moments. All of a sudden, you don't have lots of individual chlorophylls talking to each other. Now you have these massive aggregate transition dipole moments, so you have much faster transfer into the reaction center. And if you have faster transfer, you get higher efficiency, which is what we care about, because the excitons are short-lived and they would decay at some point. So you want to get them into the reaction center as fast as you can. How do we know? Why do I think this is so important? Well, we've done this study now a few years ago where we randomized the orientation on a computer. I'm a theorist, so you'll forgive me. We randomized the orientations. Instead of having these perfectly aligned circular things, we imagined what would happen if the transition dipole moments were pointing in random directions. And doing so would remove the delocalized nature of these eigenstates. And what we get is a distribution of efficiencies, which is more than 5 standard deviations below what the natural arrangement is almost double what you get if you try to randomize them. Okay, so it's in fact near optimal, the actual kind of equatorial arrangement of the transition dipole moments as you go around the ring. Okay, so this seems to be certainly better than if it was thrown together by accident. Now, I wanted to say that by the way, this was then and still is the most statistically significant coherent enhancement that has been suggested in a photosynthetic device, photosynthetic architecture. Now, speaking of devices, I've also been working on organic semiconductors, which are made of organic molecules. They're flexible, they're light, they're thin, they're colorful, they're semi-transparent, they're truly clean energy. You can print them roll to roll, and they're the closest thing we have to photosynthesis in how they operate. Now, I won't have time to go into the details, but what we've found over the past number of years is that the kind of usual approximation that people in this field make, which is the transport of charges and excitons in organic semiconductors is by hopping from one molecule to another, is not correct. I mean, obviously, we're not also in a perfectly ordered crystal where you have Bloch waves that are infinitely extended, but in reality, there's an intermediate transport regime where you have partially a little bit of delocalization, okay? Just a little bit, just like how you have only a little bit of delocalization in the LH2 in the purple bacteria. But what we find that even that small amount of delocalization, maybe over just 2 molecules, can improve efficiency dramatically. So it can improve mobilities by a factor of 10 or more over just classical hopping. It can improve the efficiency. How likely are the charges to separate into electrons and holes by a factor of 2? Okay, so here is the efficiency, and you can compare the solid line, which is the calculation involving delocalization, to the one without it. So you get massive improvements. This is completely analogous to supertransfer that I spoke about before. Okay, so those are 2 examples. We think it matters based on calculations in photosynthesis and in these artificial devices, but I promised you a classification. And this classification is based on 2 observations. The first is that coherence is a basis-dependent concept. So it depends on, you can think about the eigenstates as being superpositions of site states, but you can likewise think of the site state as a superposition of the eigenstates. So you can't really say that this is more coherent than this. It just depends on which basis you're in. So that's the first element of a classification. And the second is that you can improve efficiency in 2 ways. Either you can improve the trapping, so faster transport into the destination, or you can slow down the loss, so faster transport to the trap, or you slow down the dissipation, so even if the transport is slow, it doesn't matter. So that's the second aspect, that 2 things you can control. You can speed up the trapping or reduce the loss. And so that gives us 2x2 grid, where over here we can talk about whether which basis is the dissipation in, whether it's in the side basis or the energy basis, and which basis is the coherence in. Is it in the side basis or in the energy basis? And it turns out that you cannot have any coherent or quantum enhancement if everything is in the same basis, because then it's just diagonal density matrices. But if the off-diagonal cases you can have, and supertransfer fits down here. We're calling it a type 1 enhancement. That's where you have dissipation in the energy basis. This means that the trapping and loss happen from these eigenstates, whereas the coherence is in the side basis. So that's just delocalization. The other possibility that no one had really thought about before we tried to put this cable together is what we're calling type 2 enhancements. And those are the ones that we've kind of discovered as a result of this. And that's the idea that you can have coherences in the eigenbasis. So you can imagine, so that's the idea of saying that the site state can be represented as a superposition of energy states. And so how does that work? Well, here's an example. Imagine I have two donors and an acceptor. If I have incoherent light, that'll just excite them equally. But the one that's closer to the acceptor will have a higher transfer rate than the one that's further away. But then depending on if I have polarizations that are in phase or out of phase, I can control which side of this superposition I'm in. I can excite preferentially on the left or on the right, and in doing so enhance the rate of transfer. And it turns out that if you do that, you do get higher efficiency by up to a factor of 2. Now, this type of example might strike you as a little bit contrived, and that's because it is. This requires the dipoles to be in particular orientations, the light to be coming in at exactly the right angles. And in a sense, it is a type of coherent control of light harvesting. But you can ask, well, when is optical coherent control in general possible? Is it really restricted to these types of contrived examples? And in recent work with Eric Gauger's group, who's speaking just in a minute, the answer is yes. Optical coherent control is only possible in contrived cases, and it's never important in any sort of practical case. And the reason for that is that coherent control is lost with two things that basically always happen in realistic light harvesters, and that's averaging. So you usually have temporal averaging. You care about the efficiency averaged over not a femtosecond, but a day. And you also have orientational averaging of many components. Now, I'm being told that I'm running too fast, too slow, so I'm going to skip these, but you can ask me about it later. But the point here is, if we return to this, there's a whole bunch of different possibilities of what you might, of way you might realize quantum enhancements in light harvesting. But I would say that these type 2 ones, which are theoretically interesting, are not really practically relevant. That you could engineer them in a lab, but it would be difficult to use them for any particular purpose. There's something here called dark state protection, which I didn't get to, but this turns out to be difficult in molecules because it requires rates to be arranged in a particular way. And that leaves supertransfer as really the only credible way of doing this. In particular, Adesh is giving a talk at noon where he will give a recipe for how you can do this, how you can engineer this in a controllable way. The problem is that none of these have been experimentally demonstrated conclusively. We think, based on calculations that I showed you, that supertransfer plays a huge and decisive role both in photosynthesis and in organic semiconductors, but there's no way in a photosynthetic organism to turn coherence on and off to check whether it matters. But if you're using an engineered quantum device, you could do that, and Adesh will tell you how. So my points are, there are quantum enhancements in light harvesting, but there's few. The limitations are that you're in weak light, you're at steady state, and that means that the single exciton effects are the most important ones. Delocalization does matter, but only sometimes, but both in photosynthesis and in OPVs. And supertransfer is most likely to be the important way that if you want to use things, you can. So what are the big open challenges? Like I said, no coherent enhancement has been definitively demonstrated yet experimentally. We do think we have a recipe for how to do it controllably, and so you should see Adesh's talk. And thank you very much for your very kind attention.
Thanks, Ivan. We have time for a couple of questions, so we've got one over here and one over there. Then we'll start.
Thanks, Ivan. That's a great update of where we are in this business. So in biological systems, I can see the constraints are pretty clear, but I guess what you're trying to get to is some sort of artificially engineered device. And do more gaps open up in your table if you can actually engineer nanostructured materials to exploit quantum coherence effects, say at the single photon level?
Yes, I think, and that's kind of where we're going at. I think so yes, stick around for Adesh's talk. So I think the first thing would be engineering a controllable device with just two sites and two donors, one acceptor. I think that can be done in some types of architectures to really show that this is real. But then, yes, I think if we want to take advantage of this, we could engineer nanostructured devices that sort of imitate some of these things that we're seeing in photosynthesis that that happen naturally and that spontaneously happen in OPVs as well, but not as good as perhaps they could be.
So how ordered are the chlorophyll molecules in nature? Unless they're completely amorphous by the arguments that you presented, one should expect some supertransfer in actual plants.
So how ordered are the chlorophylls? It depends hugely on which species you're talking about. So in some species, in plants, they're actually quite disordered. The example that I showed you of purple bacteria, they're very ordered within individual rings. There's always fluctuations in these things, so they're not perfectly, they're fluctuating. So in a ring of 16, most people think that it's about 4 or 5 is the extent of delocalization around the ring. There are other examples like the chlorosomes and green sulfur bacteria, which are basically sacs of pure chlorophyll, which are thought to self-assemble into things that are essentially look like ordered nanotube structures, but there's no way to probe that reliably.